Hello, my name is Christine Albano. I'm from the Desert Research Institute in Reno, Nevada, and today I'll be talking about a preliminary analysis to assess wintertime streamflow ensemble forecast skill in the Truckee River Basin, which was completed for the purpose of better understanding the challenges and opportunities for incorporating forecast-informed reservoir operations into water management within this basin. And I'd like to begin by acknowledging my co-authors, Michael Imgarten from the California-Nevada River Forecast Center, and also Michael Dettinger with the Center for Western Weather and Water Extremes at Scripps. I'd also like to acknowledge the Army Corps of Engineers Engineering Research and Development Center for funding this work. And so I'm going to start by this presentation by describing the study area, which I suspect many of you are already familiar with, but we'll go ahead and provide a brief overview of key points for those who are not. The Truckee River originates in the headwaters of Lake Tahoe in the Sierra Nevada mountain range near the California-Nevada border. In this basin, most precipitation falls in the upper elevations in the form of snow, which feed river flows that extend 121 miles northward and eastward into the Great Basin Desert and ending at Pyramid Lake. The Truckee River is a highly managed system providing supplies for downstream municipal, agricultural, industrial, and tribal water uses, and is also managed for recreation, hydropower, environmental flows for endangered and threatened fish. Within the watershed, the upper watershed, there are 7 reservoirs in total, including 3 dammed natural lakes that are used for water supply and 4 additional man-made reservoirs that are operated for flood control, but also provide water supplies. Also of consequence, the Truckee River flows through areas of very high population density, including the cities of Reno and Sparks. And because of this, flood consequences can be very costly, with 1997 and 2005 serving as 2 examples, with the former 1997 flood having an estimated cost of about nearly $1 billion in 1997 dollars, and 2005 flood costs were around 20 to 50 million in that case. And so given that most of the water supply is generated upstream in the winter season and the greatest demands are downstream in the warm season, reservoir operations in the Truckee River Basin involve a pretty delicate balancing act between storing enough water to meet demands while ensuring that sufficient storage space remains to accommodate runoff during winter storms that would otherwise result in flooding of human-built infrastructure. As shown on the right, this has historically been managed through operations that follow the flood control curve, whereby flood control reservoirs release water in November prior to the winter season to make space for potential floodwaters, and do not begin capturing water again until April 10th, when the risks of large winter storms is reduced, but snowmelt runoff can still be captured. But this balancing act is likely to become more difficult under warming climate, as water that previously came in the form of snowfall and was stored in the snowpack will increasingly fall as rain, with the bulk of runoff occurring earlier in the year, prior to the date that current operational rules permit capture for water storage, and importantly, coincident with the timing of greatest flood risks. And so changing operations to enable earlier capture of runoff has been demonstrated as a way to resolve the water supply side of the issue, but this still leaves the flood risk side of the equation to be addressed. And this brings us to a concept called forecast-informed reservoir operations, or FIRO, that is being explored in a number of watersheds of California. And FIRO is officially defined as a reservoir operation strategy that better informs decisions to retain or release water by integrating additional flexibility in operation policies and rules with enhanced monitoring and improved weather and water forecasts. And FIRO is gaining traction as a practical alternative to increasing or sustaining water supplies while mitigating against flood risks that doesn't involve building new water storage or flood control infrastructure, which might be cost prohibitive. And so one of the reasons FIRO strategies in California have been well explored and really viewed with a high level of optimism is that flooding in California is strongly linked to atmospheric river storms. And this is the case for the Truckee River Basin as well. What we can see in this chart is that nearly all of the major floods on the Truckee River at Reno were associated with atmospheric rivers between 1948 and 2013. In addition to this, over the past decade or so, there have been really great strides in terms of forecasting and monitoring atmospheric rivers, or ARs, that make it possible to anticipate their occurrence up to a week or more in advance. And so to date, all FERO studies have been conducted on the west slope of the Sierra Nevada and in basins that tend to be more rain dominated rather than snow dominated, though there are now FERO studies being conducted in the Feather and Yuba rivers, which do have snow. And so the fact that the Truckee River Basin is on the lee side of the Sierra Nevada and has factors related to snowfall and snowpack conditions that need to be considered adds some additional forecast challenges relative to areas where FERO has already been well explored. So one of these is determining how much of a rain shadowing effect or precipitation spillover there is due to the onto the east side of the Sierra Nevada. Perhaps even a bigger challenge is has to do with forecasting the elevation at which the rain to snow transition occurs. This is always tricky from a forecasting perspective, and because a very large area of the Truckee River Basin is right at the average freezing elevation, this can lead to very large uncertainties in terms of how much storm runoff we might get. Finally, the condition of the snowpack and soils can also strongly determine how much precipitation is infiltrated and absorbed versus how much will run off. And this is not well understood or monitored at this point. So despite the significant advances we have in terms of forecasting large storms, there are factors in the Truckee River Basin that might make forecasting stream flow a bit more difficult. And so this leads to the objective of this study, which was to conduct a preliminary assessment of wintertime stream flow forecast skill in the Truckee River Basin. And for the purposes of this presentation, I'm going to focus on just a few of the forecast points, although there are several more that could be evaluated. And these were selected because they represent a range of contributing area sizes and elevation distributions, with Lake Tahoe and Sage Hen Creek representing sort of upper elevation contributing areas, Lake Tahoe being a large one and Sage Hen Creek being a rather small one. We looked at Prosser and Stampede Reservoir, which are both two of the major flood control reservoirs. And then we also looked at Truckee River at Fairhead. This is an integrator site, and the flows at this site are an important determinant of how the Truckee River is managed. So our approach involved conducting a retrospective analysis on readily available forecast data from the National Weather Service California Nevada River Forecast Center. And we looked at winter flows only, so October through April, and the years 2015 to 2019 water years. We looked at two types of forecast data, including the deterministic forecast, which is a model-based prediction of stream flow out to 5 days, which is produced by the California Nevada River Forecast Center and is represented by this black line. The second is the ensemble forecast, which provides an uncertainty range based on 60 or more individual forecasts that differ in terms of their initial conditions. And these ensemble forecasts go out to 30 days and are based at the longest lead times. They're based on the historical climatology. And as we get to shorter lead times, they integrate and weight information from other forecast products, such as the Global Forecast System, or GFS, as well as the deterministic forecast. So I'm mostly going to focus on the ensemble forecast results, since this is the product that is ultimately used for flood risk forecasting for FERO. I'll also note that given that days when atmospheric rivers are occurring are what we're most interested in, we analyzed various subsets of data, including separating out the non-AR days, and then looking at AR days when daily flows were in the top 10 percentile based on 1980 to 2019 time period, and then separating those from other AR days that were maybe more run-of-the-mill and flows were not in the top 10 percentile. For each of these subsets, we conducted two types of assessments, one related to forecast accuracy and the other related to forecast reliability. So moving on to the results, this slide is showing the forecast accuracy of the ensemble median flow prediction as a function of forecast lead time up to 16 days. And this accuracy is measured as the R-squared value between the observed and predicted 3-day flow volumes on a given day. The different colors represent the three subsets that I mentioned, including those highest 10 percentile AR days in red, other AR days in blue, and non-AR days in green. And the line in the middle represents the average R squared for a given lead time across the 5 sites I mentioned, and the ribbon represents the range across those 5 sites. And so what we see is that for the top 10% flow AR days, and to a lesser extent for other AR days, forecast accuracy clearly starts to improve, starting at about a 7-day lead time. We can also see that the top 10% AR, top 10% flow AR days tend to have lower accuracy overall relative to lower flow AR days and non-AR days. And given that this is, and you know, these are the flows that we're most interested in. With 1-day lead time, we see about 53 to 68% of the variance in observed flows explained by the predicted for that top 10 percentile flow days. So we repeated this analysis based on the deterministic forecast, though we only had these data for Prosser, Farad, and Stampede, and these are full natural flows for anyone that's meaningful for. And this is only for a 5-day lead time, since that's as far out as the deterministic goes. And what we can see here is that, again, the forecast accuracy improves as a function of lead time. And I plotted here the X's as a reference for the ensemble results on that previous slide at a 1-day lead time. And we can see that the deterministic does a little bit better than the ensemble median for non-AR days and lower flow AR days, but there is really quite a vast improvement for those top 10% flow days with much higher forecast accuracy in the case of the deterministic relative to that ensemble median indicated by the X. And this is to be expected somewhat because the deterministic forecast represents the sort of best forecast given our knowledge of the system and conditions, while the ensemble forecast is still influenced by historical climatology, even at these shorter lead times, which we're seeing is tending to bog down the predicted flow magnitudes. And you can see this to some extent in the scatter plots in this slide, where we're showing the observed versus ensemble median predicted flows for just AR days, since this is what we care most about. And here the gray line represents the 1-to-1 line, which would represent perfect accuracy. The colored dotted line indicates the regression relationship between the ensemble median and observed for those top 10% flow AR days, and the black dotted line indicates that relationship for the deterministic versus observed. And what we can see here is that the regression lines fall pretty consistently above that 1-to-1 line, indicating a bias toward underprediction. And we see that for most sites, that black line is a little bit closer to the 1-to-1 line, indicating that there's less of a bias in that deterministic forecast. And as I mentioned previously, the difference between the deterministic and ensemble forecast accuracy performance is likely driven by that influence of historical climatology on the ensemble. So the second analysis we conducted was related to the reliability of the ensemble in terms of capturing, in terms of the uncertainty range, capturing the observed flows. And this reliability assessment is achieved by ranking the observed flow at a given lead time, and here I'm showing a 1-day lead time, as relative to the predicted flows based on each member of the ensemble. We then plot a histogram of those ranks. So here again, I'm showing results for 1-day lead time, and we're looking at the top 10% flow AR days on the right and the other AR days on the left. And the interpretation of these results comes from the shape of these histograms. So what we can see here is that underprediction bias, and that's manifested as a slope upward toward the right, meaning that we have higher frequencies of observed flows that rank higher than most of the ensemble members. And we see this more so in the case of the top 10% flow days relative to other AR days. We also see that these slopes tend to be lower for Tahoe and Seichen, both sites that are higher up in the watershed. I don't know why that is necessarily, but it is an interesting result nonetheless. The other thing that you can see from these histograms is a tendency toward under dispersion for some of the sites, which is indicated by a U shape. And this comes from higher frequencies of the observed flow ranking among the highest or lowest of all the ensemble members, with ranks on the left or rightmost bins, meaning that the observed flow fell completely outside the ensemble range. And so we do see this at Stampede and Sagehen to a certain degree. And this tends to be more of an issue for those lower flow AR days on the left than for the higher flow AR days on the right. And so as a final point, and just to provide maybe a less abstract view on these results, I've plotted here the forecast and observed accumulated flows for 1, 3, and 5-day lead times during the 2017 winter, which provided a lot of opportunity to evaluate flood forecasts. And just to orient you to these plots, the black line indicates the observed flow. The solid green line in this top graph indicates the ensemble median, with the range plotted as sort of the colored bar. And the deterministic is represented by the dotted line. And these gray vertical lines indicate days on which atmospheric rivers were occurring. And so what we can see from these plots from a more qualitative standpoint is that flood peaks are generally well captured by the ensemble. Even at that 5-day lead time, we see the black line is sort of well within the color bar in most cases. And that's definitely what we want to see. And the issues related to bias and under dispersion that we saw in the previous plots are tending to occur more on the rising and falling limbs of the hydrograph and during non-AR conditions when the ensemble is narrow due to a lack of precipitation in the forecast. And so our preliminary conclusions from this work are that flood potential is clearly detectable at a 7-day plus lead time, but there is a tendency toward underprediction of flow magnitudes during high flow events, even at short lead times. And despite this, flood peaks are typically well captured by the ensemble, and it's really the rising and falling limbs of the hydrograph where forecast skill has maybe the greatest potential for improvement. And this analysis is very much still in the works, and there's a lot to do, and I'll just highlight a couple of key aspects in terms of next steps. The first is contextualizing results in terms that are relevant to the physical and operational constraints within the Truckee River system. For example, rather than using an arbitrary threshold of top 10% flows, as we've done here, as a first pass, using actual flow thresholds that are related to reservoir release or channel conveyance capacities would make these results much more relevant in terms of understanding implications for FERO. Furthermore, there's a need to translate these reservoir release and channel conveyance capacities to understand what kind of forecast lead time and skill would really be necessary for FERO to be viable. In addition to this, there is a great deal of work needed to interpret these results in terms of understanding the relative contributions of precipitation forecast uncertainty, storm characteristics, and antecedent conditions to the stream flow forecast skill results we've observed in this analysis. And so with that, I'd like to thank you for your attention today, and I've provided my email address here and welcome you to contact me with questions. I'm also happy to take any questions or feedback you might have on this work during the Q&A at the end of this session, and I hope to see you there. Thanks.